All right, hello everyone. So today we're going over a linear algebra problem. So I have the matrix A, which is 3 by 3, 3 rows, 3 columns. And reading this across the rows, first row is 7, 1, 4, second row is 2, 4, minus 6, and third row is 3, 1, 9. And we're asked to find the determinant of A, or DTA short, by using properties of determinants and row operations. All right, so here's what we have. We have a matrix A. It's a square matrix, and we're gonna look at these properties that combine, shall we say, properties that you have about row operations on a matrix and the corresponding results with determinants. Okay, so the first property says that if you have a matrix B that results from multiplying a row of A by a non-zero constant and adding it to another row, the determinant stays the same. So all this saying that if you take a matrix and you multiply a row by a number and then add it to another row, whatever that result is, the determinant of that new resulting matrix is the same as the original. Okay. Second property says if B results from multiplying a row of A by a non-zero constant, the determinant of B equals that constant times the determinant of A. So if you multiply a row of a matrix by some constant k, then the determinant of that new matrix is equal to you finding the determinant of the original times that constant. Okay, and we'll get to that. It's easier seen than reading it out loud here. And number 3, if B results from switching a row of A, the determinant of B equals minus the determinant of A. So if you switch two rows on a matrix and you take the determinant, it says that the new matrix is off by the determinant of the original by a negative. Okay. All right, so let's work that out over here with this problem. So we've got the determinant of 7, 1, 4, 2, 4, negative 6, and 3, 1, 9. So notice that you have a multiple of 2 in the second row. Sorry, that means that every entry there is a multiple of 2. So I can factor a 2 out of that row, and what that would do is it would cause now the determinant to be it's going to make the determinant be a multiple of 2 now of the original. Okay, so that's how this rule works out. Next thing I see here is where we have the second row, 1, 2, negative 3. We have a pivot of 1 here, and I like to have a 1 up where the 7 is at. So I'm going to switch rows. Okay, so I'm going to switch row 1 and row 2, and that would result in 1, 2, minus 3, 7, 1, 4, 3, 1, 9. And what that does is that you would factor like a negative in, you would put a negative in front of the 2. Okay, so that's what happens when you switch rows. You put a negative in front of your matrix. All right, and what I can do now is as follows. I can go ahead and make the position where the 7 is added to 0 and the same thing where the 3 is added to 0. So the way we do that is by multiplying the first row by negative 7 and adding it to the second row. So you would take negative 7 times row 1 plus row 2, and that's going to be your new row 2. You would get minus 2 times 1, 2, minus 3, 0. And if we went ahead and did the math there, this would be a negative 13 and a 25, and this third row stays the same. And that has no effect on the determinant of what you had in the previous step. So these two determinants are the same. And last, I'm going to go ahead and make the position where I have a 3 here to make 0. So I'm going to multiply the first row by negative 3, and then add it to the third row. That's my new third row. And that will not change the value of the determinant of the previous step. So you'd have 1, 2, negative 3, 0, negative 1325, and then you would have your result as 0 for the last row, negative 5, and 18. Okay, and that's where I would stop. Can I go further? Yes, I could go and make this, this position where the negative 5 is into a 0 and where that 18 is into a 1 if I wanted to. Certainly that's the case. You can do that. However, you want to, in my opinion, you want to do as much math as necessary for you to have a easy enough way to compute the determinant, and that's good enough in my opinion. It's at these steps. The reason for that is as follows. If you look at the remaining values we have inside that we're taking the determinant of, you can certainly expand by a row or a column, and you can expand by the first column, and that result would be minus 2 times 1 times, and the way it works is you block the row and column where this is at, minus 1325 minus 5 and 18 is what you have left. Okay, so that's what we're doing when I said block the row and column. And I will link a video to how to determine the matrix of a 3x3 and a 2x2 if you're interested, if you need to review this for this specific case. And this method will work out for any matrix here, 4x4, all the steps that we've done, 5x5, etc. So this would be negative 2. So when we do a determinant of a 2x2 matrix, we multiply these entries and then those entries and subtract from each other. 18 times negative 13 gives you a negative 234. And then a negative 125 is what we get when we multiply the 25 and the negative 5. So you get negative 2 times negative 234 plus 125, which is negative 109. Okay, and if you multiply negative 2 times negative 109, you would get a 218 here for your answer. All right, and the whole purpose of this in a way is that you can go ahead and find the determinant. It's easier using this method than expanding by rows or columns originally, because if you recall, when you expanded by rows or columns, it's very cumbersome with notation and all over the place, so kind of a bit of a time saver here. Okay, well, thank you for your time. Hope this helps.